f dash of a function f is a function or a value. So simply a derivative of a function describes how fast that function grows or decreases. So if the derivative is a constant, so derivative is like, for example, if our function is plotted as a line, and our derivative is a constant value like 5 or minus 3, then the function grows constantly at any point of its domain. What this simply says is, if your function looks like, let me find that, like this straight line, if this is your function wx minus v equals 0, then at any point of the line you can see your function is growing at the same rate. It's going straight. However, if your function looks something like this, then your, zoom in on this, like this, then it means that your function will have a different rate of change at every interval, right? So you need to take a very small interval, like from this point to this point, and that will seem like a straight line, right? Because it's such a small part of this curved line. And if you focus on that, like if you just look from here to here, it's like a straight line from 4 to 2, right? So if you focus on that part, you could get the derivative, which is simply the rate of change. And by adding these partial derivatives of every interval, you can get the overall derivative of the function. So wait a second. Yeah. So so if the derivative is a function, like I explained, then the function can grow at a different pace in different regions of its domain. So if it is something like function of x is equal to x squared, right? It then depends on your x. It then depends on your x how your variable will change, right? There's no constant value that for every 5 uh, steps in x it's moving 1 step in y. No, that's not how it's going. The rate of change is x squared. So if your x is 1, it will be 1, but if your x is 2, it will be 4. So your rate of change here, your derivative is like 3. But if you then put 3, then you will get 9, so it's now increased by 5. So it's not a constant value, it will grow or decrease at certain intervals. If the derivative is positive at some point, then the function grows at that point. If the derivative is negative at some point x, then the function decreases. If the derivative is 0, that means the function slope at x is horizontal. Simply, that will only happen like at this phase, you can see here, or this where the local minimum is. Here your derivative will be around 0 because the line becomes horizontal for a while, right? It goes straight and then starts rising again. So derivatives for basic functions are known. So we know that if f of x is equal to x squared, then f dash of x will be 2x. If f of x equals 2x, then f dash of x equals 2. If f of x equals 2, then because now it's become a constant, right? F of x, then f dash of x is 0, because the derivative of any function where the value is a constant, then your derivative becomes 0. If the function we want to differentiate is not basic, we can find its derivative using the chain rule. So I will explain the chain rule further, but for now it's simply when you try to find one derivative which is related to, so for instance, to find one derivative you need to find several derivatives. So it's like f of x equals f of g of x, right? So here what will happen is f dash of x will be equal to f dash of g of x and then g dash of x separately. I'll explain this for when we actually start applying it in neural networks. So for example, here if f of x is 5x plus 1 squared, then g of x is 5x plus 1, and when you try to apply this to this chain rule, you will get the value 2 into 5x plus 1 into 5, right? Because um, the reason I'm saying 5 is because g of x, where 5x will become 1 and 1, which is a constant, will become 0, so it will become 5 into 1, which is 5. So 2 5x plus 1, and this 2 came because it was squared over here, right? And we know that x squared becomes 2x. So in this case, if we treat this as x, then this will become 2x. So 2 5x plus 1 into 5, which is equal to 50x plus 10. gradient is so a gradient of a function is a vector of partial derivatives. So the gradient is actually the derivative at every is a, a collection of the derivative at every point, which you can use to find the way your function changes over time. And when you are focusing on a partial derivative, the other inputs we are considered as constant values, right? Because when we are talking about this partial derivative, the other inputs will have to be taken as constant. So we treat as if after this point the function is going to straighten out and go completely straight, so that things don't become too complicated and we can get the partial derivative rather than ending up computing a derivative for the entire line, which is for the entire function, which is impossible because it's not a constant rate of change. So the partial derivative is simply takes the other what do you call it, the other derivatives as 0, which as constants, and because the derivative of constants is 0, they turn out to become zeros. So if you say, if your x1 equals axa, that is, if your x1 is a, then your derivative of that function with respect to x1 will be denoted as derivative of f upon derivative of x1 equals a plus, so it's ax, which will become a because x will become 1, and then bx, which will become 0 because we are taking it as a constant, and c, which will also become 0. So a will be the derivative of the function ax1. Same for the derivative of x2 will be, the answer will be b. A random variable usually will be written as an italic capital letter, which won't be bold, so only x, right? Is a variable which possible and use element. So simply, a random variable can have any value between a set interval, right? For example, like toss of a coin, or roll of a dice. So there are some random, so it could be there are going to be random values, right? And there are two types of random variables, discrete and continuous. A discrete random variable has a limited number of outcomes possible, like you might have values such as red, yellow, blue, or in the case of rolling the dice, numbers 1 to 6, right? So the distribution of the probability of a discrete random variable, so if you want to see how the probability is for every outcome, it is easy. You just have to calculate the probability for every outcome and plot it, right? But a continuous random variable, which can have an infinite number of possible values in within an interval, obviously, like height, weight, time, right? Weight could be anywhere from 50 kgs to 100 kgs, so it has a lot of values. And if you start calculating for every value like 50, 51, 52, it won't make sense. The values will be so small, there will hardly be any difference, and using that you cannot predict anything, right? Therefore, instead of that, we use instead of plotting a PMF, which is simply you make a list of the probabilities for each outcome, which is called a probability mass function, PMF. Here example A, you can see, right, for 1 2 3 4. So but for continuous random variables we use PDF, a probability density function, right? So what happens here is the area under this curve will always be equal to 1 if you add it up, right? And what we do here is simply we create binning, which I will explain further, right? The expectation, so if we let a discrete random variable x have k possible values, the expectation of x is given by, there is this formula. So it is simply you add up x into the probability of x. So you say x1 into probability of x1 plus x2 into probability of x2, and so on, right? So in case our value here is of x is 2, so you can see the probability is 0.3, so it becomes 2 into probability of x being 2, which is 0.3, so it becomes 2 into 0.3, which is, I guess, 0.6. and that is the expectation of that variable, right? Another important statistic is standard deviation. Standard deviation is simply variance. Variance is, what is variance? Let me get to that. Variance simply tells you how much your data varies from the mean. So it is your predictions, which is x, subtracted from the mean, right? So prediction minus the mean squared, so that all the negative values, so for example your negative values shouldn't end up cancelling out your positive values and decreasing your variance, so we square them, right? And in standard deviation you put a square root on it, so it becomes your predicted values minus the mean squared. So it's square root of your predicted values minus mean squared, right? And as I told you, variance is simply predicted values minus mean squared. So for a discrete random variable, the standard deviation is given by the expectation, which is simply the probability of x being x1, into the what do you call it, the variance, which is x1 minus the mean squared, plus, and then you do it for every possible outcome, right? Where your mean, where your, what is this, I think it's called a mu sign, is equal to the expectation of x, right? The expectation of a continuous random variable is given by the derivative, partial derivative x of your function x in relation to x, and derivative. I will explain this later. Now unbiased estimators and bias rule. So what is Bayes rule? There is a thing known as a conditional probability. So a conditional probability simply means what is the probability that, given we know that x has occurred, what is the probability of y occurring? This is known as a conditional probability. Bayes' theorem simply says probability of event x occurring given that event y has occurred equals probability of event y occurring given event x occurs into probability of x upon probability of y. So probability of A given B equals probability of B given A into probability of A upon probability of B. This is Bayes' theorem. We will see where it is used. It's mostly used in naive Bayes, which we will cover ahead probably. What is parameter estimation? So Bayes' rule also comes in handy when we have a model of x distribution. So if your model requires some parameters in the form of a vector, so for example every model has some values which need to be declared, right? So like you will see in neural networks, you need to declare values like alpha, number of layers, etc. So when you want to declare these values, you will need to find the optimum parameters, and this is where Bayes' rule comes into handy, where it says that, because this function, so what we simply do is we say probability of parameters in the vector. So we can update the parameters in our vector. So the vector theta is a parameter of our model, and we can update the values of those parameters from the data using the Bayes rule. How do we do that? So we say our predicted or our current value. So what is the probability of our distribution or our data being x, right? And our value being this, value being theta hat, which is simply theta predicted, or the value we are using, is equal to the probability of our distribution being x given our parameter into the probability of our parameter upon probability of x, right? So if we have a sample S of our data x and the set of possible values for our parameter is finite, we can easily estimate the probability of our parameter being optimum by applying Bayes' rule one by one, right, iteratively for every example, like one example of the set at a time. The initial value can be guessed, like you could just guess that it's 1 or anything. So the initial value could be anything, we could guess 1 or 0, right? but then you could, change it iteratively and finally find the optimum value. So what is a hyperparameter? A hyperparameter is simply a property. So if your learning algorithm requires a property which is not exact, it's not exactly a numerical value, right? Like, it's sometimes not a numerical value, but it simply influences the way the algorithm works. For example, if you are creating a neural network, you have to define which type of neural network you are creating. Is it a convolutional neural network? Is it a recurrent neural network? Is it an artificial neural network? So here, artificial, recurrent or convolutional is a hyperparameter which will affect the way your algorithm will work. Hyperparameters are not learned by the model from the data. We need to set it before we run the algorithm, and we will see how to do that in chapter 5. Now, there are two words that will be used a lot in this book, which are classification and regression. Classification is when we are assigning a label to an unlabeled example, right? So when we have trained our model and now we are giving it data and it is predicting the outcomes. So this is a classification problem which is solved by a classification learning algorithm. Our classification learning algorithm will take a collection of labeled data that we will provide it, and then it will fit a model to the data which will learn the necessary patterns, and based on what it has learned it will then make predictions. So spam or not spam, classification of emails is a classification problem, right? There is two types of classification problems. There is binary classification where you have only two outcomes, so spam or not spam, sick or healthy, good or bad, bought or buy or did not buy, and then there is multi-class classification where you have a problem with three or more classes, like a roll of a dice, like 1 to 6, lot more possibilities, right? Regression is a problem where you are predicting a real valued label, right? So for example, you're actually predicting an actual value. So estimating house price, right, is a regression problem. So regression problem is simply where you have a continuous variable, and classification problem is when you have a categorical target value. Now there are two types of models: model based and instance based learning, right? Model based learners, they use the training data to create a model. This model will use parameters which were learned from the training data, right? So in SVM, the two parameters we learned from the training data, the best values of these parameters were learned from the training data, were W and B, right? And after the model was built, the training data can be discarded because we already have the best fitting model. Now we just need that equation. We don't need the the data of the whole training data, right? But instance based learning algorithm will use the whole data set as the model. So for example, in clustering, you know a popular method of clustering is k nearest neighbors. So in k nearest neighbors, you need to predict a label for an input example, and then based on, and how do you predict this label? So you predict it based on how close it is to a cluster of other examples. So simply there will be clusters of different labeled data points, and then you will get a new data point, and then based on which cluster it is closest to, you will assign it a label. So in this k nearest neighbors algorithm, the model remembers the training data and uses it the entire time, because the training data itself is the model. There are there are two types of learning: shallow and deep learning, right? A shallow learning algorithm will learn the parameters of the model directly from the features of the training example. So simply it will directly take the data and learn the parameter of the model from the data directly, right? Deep learning will will take the input, it will apply some transformation, some equation on it, which will improve the machine's ability to understand the relationship between the input and the output. So a deep learning model is more accurate, right? So for example, deep neural networks. So here, in deep neural networks, most model parameters are not learned directly from the features of the training samples, but from the outputs of the preceding layers. We will get to that in chapter 6, where we will have a look at neural networks closely.